All right, let's just jump right in. Did you know there's this hidden network? It operates silently, miles down in the darkest parts of the ocean, but it's what makes so much of our modern world actually work. We're talking about deep water acoustic positioning. And trust me, it's the secret sauce behind some of the most incredible engineering feats you can imagine.
So let me ask you something. How in the world do you keep a massive ship parked perfectly still over one tiny spot when that spot is miles deep in a churning ocean? Seriously, think about that. It's not just a tricky question, it's the fundamental challenge for pretty much any offshore operation. It's like you're trying to perform delicate surgery, but your entire operating room is a massive vessel being tossed around by wind and waves. How on earth do you get that kind of pinpoint accuracy?
And believe me, the stakes here are just immense. We're talking about connecting pipelines, lowering enormous structures, and servicing equipment in absolute total darkness under pressures that would crush a tank. If you're off by just a few feet, well, that could be catastrophic. You absolutely have to know exactly where everything is, sometimes down to the centimeter.
So, what's the solution? Well, on land, it's easy, right? We've all got GPS in our pockets, but the moment those radio signals from satellites touch the water's surface, they just stop. Poof, gone. They can't get through. So it turns out the answer is to use a completely different kind of wave. Sound.
And it really just boils down to basic physics. Radio waves get soaked up by water almost instantly, but sound waves, they can travel for miles and miles underwater. That simple fact makes sound pretty much the only reliable tool we have for finding our way around in the deep ocean. It is, for all intents and purposes, our underwater GPS.
The technology that makes this all happen is something you've probably heard of: sonar. The name itself is an acronym, and it tells you everything you need to know: sound, navigation, and ranging. Now, the basic idea has been around for a long time, but today's systems have turned it into an unbelievably precise science.
Okay, so at the very heart of all these sonar systems is a little device called a transponder. The idea is actually super simple, but it's brilliant. A ship on the surface sends out a sound, a ping. The transponder, which is sitting on the seabed or maybe on an underwater robot, hears that ping and immediately sends one back. All the ship has to do is measure the time it took for that sound to go down and come back, and boom, it can calculate the distance with amazing accuracy.
All right, so we're using sound to measure distances. That's cool. But how do you go from just knowing the distance to knowing a precise position? Well, that's where the two main methods, the two main tools in our acoustic toolkit come into play. Let's break them down.
So you've got two main flavors here. First, there's ultra-short baseline, or USBL. The best way to think of this is like a single, super sophisticated ear on the bottom of the ship. It can figure out not just how far away a ping is, but also exactly which direction it came from. Then you have long baseline, or LBL. This one is totally different. It's more like you're building your own private GPS satellite network, but on the ocean floor, creating a fixed grid with a bunch of transponders.
Now, you've got to pick the right tool for the job, because they each have their pros and cons. LBL, that's your high precision option. It gives you the best possible accuracy and lots of extra data to double-check everything. But the downside is it's a huge operation to set up. You have to drop and calibrate a whole array of transponders for every single job site. USBL, on the other hand, is all about speed. You just need one beacon down there and you're good to go. The catch, its accuracy is completely dependent on having really good motion sensors on the ship, and it can get thrown off by background noise. So let's dig into LBL a little more. You literally drop a whole network of these transponders onto the seabed. Once you've figured out exactly where each one is, you've created this incredibly precise local grid. From then on, any underwater vehicle just has to ping at least 3 of them. It's a lot like how GPS works with satellites, a process called trilateration, and it lets the vehicle pinpoint its own position with just phenomenal accuracy. This is really the gold standard when you're doing heavy construction, and you need things to be perfect. USBL, though, is a completely different beast. It's built for speed and flexibility. You have one single unit on the ship's hull, sometimes it's no bigger than a bowling ball, and inside it has a whole array of tiny underwater microphones. By measuring the microscopic differences in time it takes for a return ping to hit each of those microphones, it can calculate both the distance and the direction to the transponder. It's ingenious, but it also means it has to be tied into the ship's motion sensors to constantly correct for every tiny pitch and roll of the vessel. Okay, so we get the tech, right? The how it works. But now for the really cool part. What can you actually do with this stuff?
This is where it all gets real, where the theory slams into the harsh reality of deep-sea engineering. And honestly, the applications they're mind-boggling.
And this brings us full circle, right back to that first question I asked. The solution is called dynamic positioning, or DP for short. It's basically the magic that keeps a ship perfectly still. The acoustic position data, whether it's from a USBL or an LBL system, is fed straight into the ship's brain. And that computer then works constantly, automatically firing the ship's thrusters in every direction to fight against the wind, the waves, and the current. It holds that massive vessel in place over a single spot, often with an accuracy of less than a meter. It's incredible.
Another huge one, and this is absolutely critical from a practical standpoint, is riser monitoring and construction. So you have these gigantic pipes, called risers, connecting a platform on the surface all the way down to a wellhead on the seabed. They're under incredible stress. So they attach acoustic transponders all along these risers to constantly monitor their shape, making sure they aren't being bent too far by deep ocean currents. And it's this exact same tech that lets them guide equipment that weighs tons and tons into place with centimeter-level precision. No room for error.
And of course, there are the robots. None of our amazing deep-sea robotics could exist without this. I mean, think about it. How do you fly a remotely operated vehicle, an ROV, when it's in total darkness miles below you? Simple. You strap a transponder to it. Acoustic positioning is literally the only way for the pilot on the surface to see. It tells them exactly where their little robot is, what it's looking at, and how it's working on all that expensive subsea gear.
And the list just goes on and on. You use it to lay pipelines along perfectly straight lines on the seabed. You use it to position towed sonar fish for mapping. It lets engineers find and re-enter a wellhead the size of a dinner plate years after it was drilled. You can even use it to send data from sensors on the seafloor back up to the ship, no cables required. I mean, it is just an incredibly versatile piece of technology.
So when you take a step back and look at the big picture, you start to see what this really is. It's not just a bunch of clever gadgets. It's a dynamic, invisible network of sound that we can basically spin up on demand anywhere in the world's oceans. It's how we extend our own senses, our own hands, into an environment that we could never, ever master otherwise.
Really? From getting energy from deep offshore fields, to doing cutting-edge ocean research, to laying the fiber optic cables that connect our world, this technology is the silent partner behind almost everything we do out there. It has literally allowed us to build an entire industrial civilization in the deep ocean, which leaves you with one really exciting question. Now that we have this power to see and build in the dark, what are we going to build next?